which is the central limit theorem for Gaussian polynomials. And as usual, stop me if you have a question. So what I'm going to describe today is joint work with Rocco Cervedio, though parts of this work draw heavily on tools which were joint with Rocco Cervedio and Elias Diakonopoulos. So the central object of study in this talk are polynomial threshold functions. I'm sure all of you know what they are, but let me anyway define them. So they're Boolean functions with the domain r to the n, and they're functions of the form sine of a polynomial. So visually, if you think about it, they look like a curve in the space. All points above the curve are marked positive. All points below the curve are marked negative. And for most of this talk, okay, for the first part of this talk, we are going to restrict the domain to, instead of whole of r to the n, we are going to restrict the domain to the Boolean hypercube, and the underlying distribution will be the uniform distribution on the hypercube, okay, whenever I talk about the distribution. And while in principle you can study polynomial threshold functions where the polynomial is of arbitrary degree, it's not very useful to do that, because at least if you consider Boolean functions over the hypercube, you can always represent Boolean functions in the form as a polynomial threshold function with the degree blowing up to maybe n. So throughout this talk, we are going to think about polynomial threshold functions where the degree of the underlying polynomial is a constant, as an absolute constant. Okay. So again, I'm pretty sure all of you know this, but polynomial threshold functions have been studied extensively in complexity and in learning theory. Complexity, there are various reasons. Learning theory, probably one of the reasons is that we can pack learn polynomial threshold functions using linear programming. So it's a good learning primitive to have. And the reason why they're again like a class of functions which are well studied is because they have a lot of structure. So we are trying to understand functions of the form sine of a polynomial, and polynomials themselves have a lot of structure. So even after we add this discontinuity kind of, we add this non-smooth, we compose it with this non-smooth thing, they still inherit a lot of structure. Okay. So now what's the question we are bothered with? So the question we are interested in is deterministic approximate counting for polynomial threshold functions, or de-randomization of polynomial threshold functions. Or in other words, we want to understand the following question. Given a polynomial of constant degree, given a polynomial, okay, let's say over the Boolean hypercube, where degree of p is a constant, compute the probability that px is greater than equal to 0 deterministically up to an error epsilon. And ideally, we would like the running time of this we want to compute this probability up to an error epsilon in time. Ideally, we would like the running time to be something like poly n to the d over epsilon. N to the d because the polynomial itself is of size n to the d. There's a description size of the polynomial. It has n to the d coefficients. So we would like the running time to be polynomial in n to the d over epsilon. But it may not be possible to achieve this. This will be a great result if we could have achieved this. So we try to do as well as we can. But the main task is we want to compute this probability up to an additive error epsilon deterministically. Doing it with randomness is very easy. You should just sample some points on the hypercube and see what fraction of times. The empirical estimate is a very good estimate, as usual. Okay. Or in other words, we're basically trying to see what fraction of times is the polynomial threshold function sine of px equal to 1. So this is the question we are concerned with. Okay. And there has been a lot of work in this area. So when I say deterministic counting, when I say we want to approximate this probability deterministically, there are two kinds of things one can do. One is oblivious counting. I want to get the spelling right. Oblivious counting, and another is non-oblivious counting. I don't think this terminology is standard, but let me define what I mean by this. So oblivious counting will be the following: that you construct a distribution D sampleable with few bits, few meaning again few bits. Ideally it will be something like order D log n plus log 1 over epsilon maybe. That will be the ideal thing, but whatever you want to do, whatever howsoever well you can do, that's better it is. Such that for all polynomials P of degree D, probability that the polynomial is greater than or equal to 0 on the Boolean hypercube under the uniform distribution is epsilon close to the probability that when you sample a point from D, Px is greater than or equal to 0. Now, the reason we call this oblivious counting is that you are producing a single algorithm that, because D is sampleable with a few bits, you can just go over all possibilities of D in time which is 2 to the number of bits. So, that is like n to the D times epsilon something, and poly n to the D over epsilon. And you can just check what fraction of times polynomial was greater than or equal to 0. And because of this guarantee, you know that's a very good estimate for the uniform distribution as well. This is called oblivious counting or pseudo-random constructing a pseudo-random generator, because you're just exhibiting a single distribution. You don't even need to look at the polynomial per se. And non-oblivious counting is any other counting algorithm which doesn't look like this. You can do anything you feel like. You can look at the polynomial, you can process the polynomial. And for this talk, we are not going to distinguish between these two things. In particular, the counting algorithms we are going to give are going to be of this form, non-oblivious counting. But it's very, very interesting to get similar guarantees for oblivious counting, even though I don't have any idea how to do that. Okay, so non-oblivious counting is anything else. Excellent. So now a bit of history. So this area has seen quite a bit of activity in the last few years. So most of this stuff started with this paper in the activities in the recent last few years started with this paper of Servideo from 2006, where for the case for D equals 1, he gave a running time, he gave a deterministic approximate counting algorithm for degree only D equals 1 polynomial. So that's like linear threshold functions, which had a running time of order n square times 2 to the poly 1 over epsilon. This was 2 to the 1 over epsilon square. I think it's order n square, maybe even order n cube, I don't quite remember. This was the first paper in the series of works. And then there was an intense amount of activity achieving very impressive results. And the last word for D equals 1 was these joint independent but concurrent papers by Harsha, Clivens, and Mecca, and Stefankovic, Wengpala, and Vigoda, I think maybe 11, where they got a running time of n over poly n over epsilon. So that's really impressive. That's really optimal up to polynomial factors. In fact, even more, they showed for D equals 1, they can approximate this probability not only up to an additive error epsilon, but multiplicative error epsilon. Doing it even with randomness is a very tricky job. If you want to approximate this probability up to multiplicative error epsilon, the first algorithm came only in 1999 by Ben Morris and Alistair Sinclair, and is based on very sophisticated Markov chain ideas. So even doing it with randomness is very impressive, and doing it without randomness is it's not very hard, but it's very tricky. It's a very impressive algorithm. No. For multiplicative, you can never do it non-obliviously. You have to. The first one or the second one? The second one was multiplicative error, and it was non-oblivious. I think at some point people started just concentrating on multiplicative error. In between, there were results which were non-oblivious with additive error. There were also concurrent works which were non. Okay, so I think the best non-oblivious for linear threshold functions is I think Mecca Zuckerman. Sorry. This is non-oblivious. The best oblivious result for Mecca this is oblivious. The best for linear threshold functions, which is an oblivious result, uses seed length, which is log n plus log square 1 over epsilon. So if you consider the running time, it's poly n times quasi polynomial in epsilon. Poly n times quasi polynomial in epsilon rather than polynomial in epsilon. This is oblivious, and the best non-oblivious is poly n over epsilon, plus it has multiplicative guarantee. For degree d greater than 1, it's impossible to achieve multiplicative error with or without randomness, because just detecting whether there is at least one solution if a polynomial threshold function is at least 1 at one point on the hypercube versus no points, that's NP hard to distinguish. You can encode max cut. Okay. So for polynomial threshold functions of degree d greater than 1, you will have to forego multiplicative error guarantees. You will have to concentrate only on additive error guarantees. For LTFs, non-obliviously achieving multiplicative error guarantee, I don't think that's possible. Yeah, because it can be that there is a very sparse set on which the LTF is 1. 1 point, yes, 1 point, yes, 1 point. So how will you ever, like, doesn't matter what distribution you choose, how will you ever hit that 1 point? Right. So non-oblivious, obliviously getting multiplicative error guarantees and even in LTFs is impossible, but it's very amazing that you can get this looking at the linear threshold function can do something. Okay, so for d greater than 1, there have been a series of papers, half a dozen probably by Daniel Kane, but oh, this is being recorded. And the first paper was by Mecca and Zuckerman, the same paper. They had both these things. And the running time, so Mecca Zuckerman had something, all these papers by Daniel Kane, and Mecca Zuckerman, they're all about oblivious counting. So they achieve this kind of counting, oblivious counting. But the running time is n raised to some function of d and epsilon, okay? And the latest and greatest by Daniel Kane achieves something where this function f is polynomial in d and subpolynomial in epsilon. But the important thing is that the running time is of this form. And the thing we want to achieve in this talk is a running time of the form n to the order d. N to the order d is really necessary. This is the input size times some function in d and epsilon. In other words, we would like the running time to remain some polynomial in n, even for some tiny subconstant value of epsilon. Having a running time of this form can never achieve this. If epsilon is subconstant, you will make the running time super polynomial. Okay, so this is the kind of thing we are interested in doing in this talk. Okay, and indeed we achieve this. That's probably the end of the thing. But unfortunately, the error we will be able to tolerate epsilon will be some inverse Ackermann type kind of thing. So it is a really poor decomposition. But that's the kind of thing we want to achieve. Is the state of the art clear? Or at least what we want to achieve? Andy?
Last two, the n to the f and e and epsilon 2, that's from a PRG. That's 2 to the c.
Yeah, that's the 2.
But yours is going to be just a non-adaptive algorithm.
And mine is going to be a non-oblivious algorithm. Yeah, I don't know how to even do this with obliviously, like get running time of form n to the d times ft epsilon. I don't even know. For like that you cannot do this? Oh, no. I mean, you can, well, I mean, if you believe that P equals BPP, you can do this. Or if you believe strong circuit lower bounds, like the Impagliazzo-Wigderson style, then you should believe that we can do this. In fact, with n to the d times poly 1 over epsilon.
Okay, but the circuit describe a PPF of degree d, as you say, is like n to the d size.
Yes, so we have the n to the d times some function of epsilon. I mean, if you believe Impagliazzo-Wigderson, the hypothesis circuit lower bounds that sub-exponential size circuits cannot capture whole of exponential time, then you can get this poly in d in 1 over epsilon.
But also not explicitly, there should unconditionally exist PRGs for these classes.
Oh, yeah, unconditionally, but not efficiently constructible necessarily. Not efficiently constructible. So yeah, unconditionally, if you choose a random set of size, the right size n to the d times poly 1 over epsilon. You should be able to get this. Yeah. Okay, so this is what we want to achieve. I hope the state of the art is clear. Okay, so now we come to okay, so now we come to the plan for the talk. The first thing will be that instead of estimating probability x in minus 1, 1 to the n px is greater than or equal to 0, we will instead estimate probability x drawn from a standard normal px greater than or equal to 0. So I'll show how to reduce this problem to this problem. Just sketch the reduction. The next thing will be showing a central limit theorem for small low degree polynomials. So even if you don't care about de-randomization, this is entirely independent of everything that is done before. And hopefully, and the CLT will roughly state, I'll define what I'll mean by eigenregular polynomials, but it will say that if a polynomial satisfies a condition called eigenregularity, which is efficiently checkable, then the law of a polynomial under the Gaussian distribution looks very close to a Gaussian itself. And this is like a tight condition. And the third thing will be, which will be the next part of the talk, that how any polynomial can be decomposed into eigenregular polynomials. Okay, so that's the plan for the talk, and most of this talk we are just going to do these things. Okay, so first thing is, before I address this reduction, why do we want to change inputs from Boolean to Gaussian? And there are two reasons really. One is at a meta level, the Gaussians have an inordinate amount of symmetry. That should be something useful to work with. At a more concrete level, the reason why it is hard to understand this function, what fraction of times a polynomial is greater than or equal to 0, is the non-smoothness here. That you're literally saying what fraction of times is the polynomial greater than 0 versus less than 0. You have to make your decision in a very short interval of size 0. And somehow if you could have said that there is not too much action happening near the interval, you would have been better off. If there would have been no, if either polynomial is always greater than 1 or less than minus 1, that would have been a great situation. Then you kind of, you're trying to understand some smooth function of the polynomial. So if you assume the underlying distribution of the polynomial is a Gaussian, you can somehow show, there are theorems which show, and I'll write some of these things, which in spirit say there's not too much action happening near the boundary. So something related to Gaussian surface area, something related to Gaussian surface area, but more like Gaussian anti-concentration. Okay, I'll actually give the statements which kind of justify why we care about understanding this. And then today's talk mainly will focus on this part. Okay, so first I'm going to really roughly sketch this reduction, but this will also give me a chance to introduce some of the tools that are very much used in this area almost regularly as a routine thing. So also give me a chance to do that. And now, as per usual, I'm going to move non-linearly. So okay, so excellent. So let me introduce some of the tools that are regularly used in the area. One is this theorem of Carberry and Wright. This is from O1, and this says the following. Let P be a degree D polynomial such that variance of P is 1 under the Gaussian. So when you endow the input with a Gaussian distribution, it's a random variable. Px is a random variable, and you normalize so that the variance of phi is 1. And then the Carboy-Wright theorem says for every theta and epsilon greater than 0, theta can be anything, epsilon has to be greater than 0, the probability that fx, this is px minus theta is less than or equal to epsilon is upper bounded by d times epsilon to the 1 over d. Meaning you choose any threshold theta, let's say equal to 0. The probability that px lies epsilon close to 0, lies really close to the boundary, is really small. So that's why we are, no such statement is true for if the underlying distribution was Boolean. If the underlying distribution was uniform on the hypercube, it can happen that with probability half the polynomial is 0 or something like that. So this partially justifies why we are looking at Gaussian polynomials, because there is this nice condition that the polynomial cannot be super close to 0. That means you can use some analysis. This is not such a non-smooth thing you're dealing with. So this says not too much. There's Gaussian polynomials are anti-concentrated. There is not too much mass in a small interval. On the other hand, there's also hypercontractivity, which says Gaussian polynomials aren't super far out from the mean. So this is hypercontractivity. I don't really know who proved it first. It's a checkered history. Contractivity. But a consequence of hypercontractivity is the following, that if you take a degree d polynomial, then the probability that it deviates from its expectation by t times its variance is at most e to the minus t to the d over 2. Okay? So if it were a linear function, then Chernoff bounds say that the probability that a linear function will deviate from its mean by t times its standard deviation is at most e to the minus t square over 2. Since you are dealing with larger degree polynomials, it has to become d. Now you attenuate the factor instead of t square, t to the d, 2 over d. But it still means that there is an exponential decay. Okay? So it means that polynomials aren't super crazy. Or in other words, the moments of polynomials, of low degree polynomials, are bounded in terms of the second moments. There is some relation. It is not that the second moment is 1 and the fourth moment is a trillion. It cannot be like that. These are both individually tight. Yes, these are both tight. I probably have an example. These are both tight. These are both tight up to like constant factors. What tools do they use? Oh, I have no idea. Something from convex geometry, I believe. Though there is an easier proof by Shaha-Lovett, which doesn't achieve this Stronger theorem, but I don't know how they prove this. I have no idea how they prove this. Okay. Yeah, both these terms are reasonably tight, like almost exactly tight.
So do they imply one another, or are they completely independent?
No, I don't think this implies this or this implies this. Like, I mean, this is saying there's not too much mass in any interval. This is saying more like, and this is saying that it's not too far out from the mean. So these are like completely different statements. I don't think they imply one another. Okay, so these are two tools which will be very helpful, which are always used in this literature. So now I want to say, now remember why I'm motivating these tools is to do the first step, which is how can we go from Boolean inputs to Gaussian inputs. So the most important primitive, or the thing which suggests how to go from Boolean inputs to Gaussian inputs, is the invariance principle of Mossel, O'Donnell, Oleshkovich. And for that, I need to define another quantity, which is the influence of a variable in a polynomial. I'm sure all of you know that, but it doesn't hurt to define. Can I write on this? Okay, people have written on this. Yeah, that's fine. I don't think I'll need it. So again, we have a polynomial p from r to the n to r. And for the first part of the talk, since we are dealing with uniform distribution on the hypercube, we can assume the polynomials are multilinear. Means no monomial has a variable with degree larger than 1, and that is enough. You don't need to consider non-multilinear polynomials over the Boolean hypercube, because xi square is 1, right, for any Boolean variable. So consider polynomial p, and variance of p, let's assume again variance of p is 1. Then the influence of the ith variable in p is just p hat square s. So px it's a multilinear polynomial, right? So I can represent the polynomial in the form I can represent the polynomial in the form xj j in S. I can consider all subsets of n. So since px is a multilinear polynomial, I can identify each coefficient with a subset of 1 to n, and let c sub s be the corresponding coefficient. X sub j is the product of the variables in S. Then influence of the ith variable in p is the sum of squares of all the coefficients to which I belongs, to all sum of squares of all the subsets to which I belongs. Okay, and the invariance principle there should be an automatic switch to do this. Sorry?
Yes should be P to S. No, P hat S. Because
Oh, right. So this is the problem with having an audience which knows everything, because then there is no confusion. I'm repeating myself over and over again. This is the problem. Anyway, what's the invariance principle of Marcel-O'Donnell, Leshkovich invariance principle? So of course there are like tons of formulations of this principle. Let me list out the simplest, since I'm not going to use it full. I'm just going to sketch it out really, but it's good to have it written down. So let P be a polynomial, degree D, multilinear, D is constant, multilinear, and maximum over I influence of the ith variable in P is at most tau. Then probability x in minus 1 to the n, Px is less than equal to theta minus probability x in the standard normal, Px is less than equal to theta, is upper bounded by d tau 1 over 8d. So yes, I got the thing correct. So this is basically saying, okay, if the polynomial was such that not just it was degree d and multilinear, but rather all the variables have small influence, then indeed these two probabilities are the same up to a small error. And since we are interested in approximate counting up to a small error, we can just move from Boolean to constant. So okay, so this suggests that okay, if we want to do it for general polynomials, we should show how to take an arbitrary polynomial and decompose it, write it as low influence polynomials, and then our reduction will be complete. And now I'm not going to do the proof really, but I'm just going to sketch out how to do this proof. There are several of these so-called regularity lemmas in this literature. I'm just going to not do any of them. I'm just going to sketch the common idea behind all of them. And the regularity lemma the aim of the regularity lemma is to do something like this. You take a polynomial Px, okay, and you construct a tree. The important parts are that the depth of the tree will be, you will choose some error parameter epsilon, and the depth of the tree will be some constant in d and epsilon. Okay. Each of the variables will be labeled by, each of the edges of the tree will be labeled by, let's say, some variable x1 equals 1, x1 equals minus 1, maybe here it's x5 equals 1, minus 1 x5 equals 1, here might be x7 equals 1, x7 equals minus 1 something, such that if you just go to the bottom of the tree, you have the leaves which are the polynomials you will obtain by restricting these variables along these edges, and all these polynomials, just as a first approximation, all these polynomials will be epsilon regular. It's not fully true. The polynomials can be either epsilon regular or super biased, that the sign is always 1 or minus 1, but let's just say it's epsilon regular. I'm not going to do it. Oh, epsilon regular, sorry, epsilon regular means regularity will be a term overloaded in this talk. For this part, I just mean the max of influence is epsilon, max of influence of all the variables in epsilon. So this is useful for an approximate counting problem, because you can, instead of counting the probability that px is greater than or equal to 0, you have now reduced the task, because this is a decision tree. You can just reduce, you have reduced the task to computing the probability that these polynomials are greater than or equal to 0 at an overhead factor of 2 to the depth of the tree, which is a constant. So you don't really care. So this regularity lemma, and as long as this regularity lemma is constructive, meaning we can actually construct the tree in polynomial time, it means that we can just focus from now on computing the probability that a polynomial is greater than or equal to 0 under the Gaussian distribution. Make sense?
So do you just pick the variable with calculator for all the split?
Yeah, kind of. It's almost the same thing. You have to sometimes pick a chunk of variables with large influences and restrict all of them. The basic idea is exactly yes. If what is the why is the polynomial not is not such that all the variables have small influence? Is because they are variables with large influence. You should restrict them. It's more like a task of, it's a tricky, I mean, sometimes it's tricky to do the bookkeeping correctly, like everything will terminate, and once you restrict a variable, the main issue is this. In a linear function, when you restrict the variable is killed forever. That's true for quadratic or higher degree polynomials as well. But that variable, killing that variable, doesn't change the influence of the other variables. On the other hand, if you have a variable of the form x1, if you have a monomial of the form x1, x2, when you restrict the variable x1, depending on what value it took, now the influence of the second variable x2 now, I mean, the variables can shoot, the influences can shoot up. So it's a tricky task to monitor all of these things. The intuitive idea is whatever you're saying. So I can do two things. It took me longer than expected to do this part. Either do you want to know the sketch of the proof, or you can directly, we can believe this is true, and then basically in tandem you use these two facts to show the regularity lemma. Either I can try to sketch the proof in next 15-20 minutes, or we can directly jump to the central limit theorem. You go fight it out for 2 minutes and you want to see the proof? Okay, I won't do the proof, but I can at least sketch the proof.
Is there a reason it's called regularity lemma?
I guess all these things are called regularity lemmas, right? You assume that something is a regular structure. It might, some sort of notion of pseudo-randomness. And here the notion of pseudo-randomness we are using is that all variables have small influence. Now regularity lemma, I mean, for Zemeri's regularity lemma, it's the notion of pseudo-randomness is the cuts are of the right size. Here it's something else. We will use other decomposition ideas later in the next part of this talk. Anyway, so the basic idea behind proving the regularity lemma is the following. Okay, once we finish this, we can take a break and I can erase all the stuff on the board. The basic idea is the following. Assume the variables are arranged in such a way that influence of one, the first variable is greater than influence of the second variable, and so on. Okay? So the variables have been renamed so that the influences are in decreasing order. Okay? And now since this influences, the maximum influence is not tau, that means that that in fact, so okay, what we do is we say consider the value of inf of I of p divided by j greater than equal to I inf of j of p. Okay. And we check, we find the first index I such that this is less than equal to tau. So note that earlier we were dividing it by the variance. So when we said the variance was 1, if the variance is 1, the sum of the influences is certainly bigger than 1. Okay, so the first variable, it might, okay, sorry, I'm being a bit confusing here. So I know influence of 1 of p. The reason that this is not already regular is because this quantity must be greater than tau. We actually don't require this quantity to be greater than tau, is not such a big issue. The thing we are more interested in is if influence of 1 of p divided by sum of all the influences of p is bigger than tau. If it's less than tau, anyway, the things will work out correctly. So let's assume that this is greater than tau. Okay. So then you now check whether influence of the second variable divided by the influence of all the variables starting from 2 to pn are all bigger than tau. You keep going, and at some point you will definitely find a variable such that influence of I of p divided by influence of all the variables after it in that order is smaller than tau. If you don't find anything, that's great, that's also fine. But find the first such index, or say it's infinity. Okay? And the first such index, okay, so the first index min of j, okay, no, so j such that the smallest j such that influence of j of p divided by k greater than equal to j influence of j and p less than equal to tau is called the tau critical index of this polynomial. Okay, so it's the first point after which the variables start looking more or less regular. Okay, and then you consider, you choose some threshold capital K. I'm writing too big, I think. You choose some threshold capital K, and K is some, I probably have it written down somewhere. It's some function. It's some function of d and maybe d over tau or something. Something I was supposed to have it written down. Okay, it's some function of d and tau. Okay, we choose some threshold. You fix some constant value k, and then you ask the question: is the critical index larger than this number or smaller than this number? Okay. If the critical index is larger than this number, means the first k, at least the first k variables, they all have very large influences. There are lots of variables, like a substantial number of variables with very large influence. Okay. Call these variables x1 to xk as the head variables, and all variables beyond it as the tail variables. The polynomials, I split the variables into x head and x tail, and then I can say the polynomial is of the form q of x head. So the part of the polynomial which just depends on the head variables, and the part of the polynomial which depends on both the head variables and the tail variables. If the critical index is large, the main thing you want to show is that because the critical index is large, meaning the first few variables have so much influence that with high probability what will happen is that q, the sign of q, if you fix all the variables in the head, the sign of this will be huge compared to this part of the polynomial. So most of the time, if you just look at the sign of this part, q of xh, that will determine the sign of the whole polynomial. What you will say is that if the polynomial is non-zero, if the polynomial is such that it's super biased, you can replace it by some other regular polynomial which is also super biased. Regularity is not a function of the threshold; it's a function of the influence of the variables.
So you get the better constant than by doing it all the way.
Sorry?
So you will get a
Which better constant? I'm doing it all the way. What do you mean I'm not doing it?
Stopping it if it's very biased.
Oh, even the existing regularity lemmas, they stop if it's super biased. They don't actually produce all the leaves to be.
But is it possible to do this?
I think it's possible to do this. Yes, I think it's possible to do this, but I'm not producing anything. I mean, we just use it as a black box. We're not trying to even optimize the numbers. I don't think it's possible to optimize the numbers, not in of a way. But the main part is that the threshold, if the critical index is super large, then you have lots of variables with very high influence, and then this head part almost determines the sign of the rest of the polynomial. With probability, let's say 0.1, this will happen. Now, this is good enough, because if it happens with probability 0.1, then you should repeat this decomposition again and again. Okay, and after a while, you will be succeeding with probability 99%. The other part is what happens if the polynomial is if the critical index is small. So this is very small. The number of variables here is like 1 or 2 or something like this. Let's say this is the case. Then, by definition, like we know, the variables here, this is a regular polynomial, because the influence of all the variables is small. The influence of all the variables in T, the influence of any variable in T divided by the influence of all the variables in T is at most tau. We know that. The only thing is that if you restrict all the variables in H, it can happen that the influence of the variables in this part may go up or down. Something bad happens. And what you do to control that is basically use hypercontractivity. You observe that the influence of a variable is itself a polynomial, and you can use hypercontractivity and this anti-concentration in tandem and show that you will still succeed with probability 0.1. So doesn't matter whether the critical index is large or small, at least on 0.1 fraction of the leaves, when you do restrict the head variables, you will achieve one of the conditions, that the polynomial is super biased or that the polynomial is regular with probability 0.1. And then you repeat it a few times. You can recursively repeat it. And after a few steps, you can stop. This was a super vague sketch of the regularity lemma. I don't want to spend too much time on it. I don't know if I succeeded in doing that. If you have any questions, I can answer that, and then we can take a break, and we'll come back with the central limit theorem.
So what's the expression for the polynomial,
The influence polynomial, see, the influence polynomial is CS square, right? This is the influence of a polynomial. Now, if you think about a restriction, right? So then, this is the value of the influence of the polynomial in the variable I in the polynomial P. Okay. Now, I can write this part. Let me use a purple marker. As I can divide it as CS. Let's say the part of the polynomial H intersection S and rho S minus H. I can divide the. What I can do is, when you okay, I want to say something here. What happens when you restrict the okay, when you restrict the variable, when you restrict a particular variable, when you restrict a particular variable in the head, what happens? There will be collapsing of the coefficients, right? So if you restrict the variable 1, then it will become now a constant. So instead of summation of CS square, you will first add up all the coefficients which become the same subset once you restrict the first variable, and then you will take a square. So you can write down a polynomial expression for that. I'm not able to write it down correctly right now, but it's a polynomial expression of degree d in the variables you have restricted. And then you can use hypercontractivity to show that it's again still a polynomial of degree 2d, and so this will not vary wildly. I have not written this part correctly. I think what should happen is that now it should become CS rho of S intersection. Okay, I'm not able to write this correctly, so might as well not write it. Okay, but you can it's a polynomial. Should we take a break now? Or are there any other questions?
So yes. Is there an expression for this order O?
Yeah. It's the expression I have this number is 1 over epsilon. So, the regularity you are shooting for is epsilon, or saying that you are happy if the function is epsilon close to being a constant is the best known is d 1 over epsilon d log 1 over epsilon to the order d. This is the number we have. Yeah, the reason I did not write it is that much later in the decomposition we'll have Ackermann type factors floating around. So, exponential is really nice in that comparison. Anything, even a tau exponential looks nice.
So you're looking for some stronger regulators.
Oh yes, this part, any polynomial can be decomposed into eigenregular polynomials. This is the part which will incur the biggest factor. These two factors are nice. This is the part which will have an Ackermann type factor.
Or would you think of eigenregulars as much better than?
Okay. Variables, when you have Boolean variables, then we are saying all variables have small influence, right? And once you consider the Gaussian distribution, a variable is the same as another linear form, because all linear forms look the same under Gaussian rotation. So, the kind of influence we'll be hoping for is that all linear forms have small influence. So, this is the kind of strong regularity we'll require to for the central limit theorem to kick in, because you see, I mean, this is a very good question. There is no distinction between a variable and another rotation of another linear form with norm 1 under the Gaussian distribution. They all look the same. So, whatever regularity you are shooting for better be something which respects this. So, what kind of regularity we will be shooting for is all linear forms have small influence. Plus, there will be like a huge qualitative factor we will require. Okay, so maybe I'm going to stop now. So, maybe one line about why this decomposition is complicated. Any regularity lemma usually has a quality of the parameter, has a quality of the parts, and the number of parts. Let's say the Zemerides regularity lemma. The number of parts you have and the quality of parts is like the pseudo randomness condition. And these are competing parameters, and they should be. They cannot be like two free parameters. You can't choose one to be 2 and another to be 100. That's not how it works. What we will require here is that will require the number of parts we'll create, the number of polynomials we'll create, and the eigenregularity parameter to be essentially free parameters. The only way we will even conceivably do this is that we'll say it is not the case that a polynomial can be decomposed into 100 different polynomials, all of which are 1 over trillion eigenregular. You can't choose these parameters arbitrarily, but we'll say maybe this is possible, and this is what we'll show, that you can always perturb the polynomial by a bit, which is okay for us, and then the two parameters, the number of parts and the eigenregularity of each part, will be free parameters. So, this thing that we need them to be non-competing parameters, essentially we need them to be free parameters, is what will blow up the complexity of the regularity lemma. Okay. Are there any other questions, or should we take a break and move to the next part? Any questions? I can answer this. Okay, no questions. Excellent. Okay, great. Let's take a break for 5 minutes. Yes, yes, yes. We will. I'll define all that in the next one. So now our task is really to understand the probability that a polynomial under the standard normal is greater than or equal to 0. Okay, and what we want to understand is a central limit theorem for Gaussian polynomials. So let me say what I want to say what do I mean by that? So suppose your polynomial was a linear form, okay? And let's normalize it. So the sum of squares of the coefficients of the linear form is 1. And they ask you what fraction of times is this polynomial greater than or equal to 0, greater than or equal to theta? It's an easy question. There is no n here. It's like you just say what's the mean and the standard deviation. You can compute that and then just check what is the probability at the normal with that mean and standard deviation is greater than or equal to theta. Up to some error, up to some arbitrarily good error, you can compute that in constant time. So that is great. So in other words, we are saying a linear form of a Gaussian is distributed like a Gaussian if you take the mean and the mean to be 0, variance to be 1. Otherwise, you scale up the mean and the variance, whatever it is. And that would be great. Like if such a law was true for higher degree polynomials, then at this point we would have just done a constant time computation. Unfortunately, and of course, that's not really true. So we want to know what about higher degree polynomials. And so of course, no such law is true for higher degree polynomials. So it's easy to see that. So suppose we consider the law of x square, if x is distributed like a Gaussian, x square is the chi-square distribution, is constant far from any Gaussian. So that's not really true, that and not arbitrary polynomials of Gaussians don't look like Gaussians, that's an obvious fact. But what about special polynomials? So consider a quadratic polynomial which is not genuinely quadratic. Let's say it's of the form summation lambda I xi square. It's a quadratic polynomial with no cross terms. Then the law of this polynomial, see, we are just adding up independent random variables. Then by the Bezier-Sain theorem, you can say that the distribution of this polynomial is close to the normal with the right mean, which is summation lambda I, and the right variance, which you can again compute as twice summation lambda I square, up to an error of maximum of absolute value of lambda I divided by square root of lambda I square. Meaning, if all the lambda i's are reasonably small, then the law of this polynomial is close to a normal in the Kolmogorov distance. So everybody knows what Kolmogorov distance is? You can just write it down. X and y are said to be epsilon Kolmogorov close if probability x less than equal to theta minus y less than equal to theta is at most epsilon. Okay? So that means the CDF at no point between x and y differs by more than epsilon. So, well, this is just the central limit theorem, that if all the variables have reasonably small influence, then the law looks like a normal. Now, that's not really a genuine quadratic polynomial, so we are not doing much. But this is where Gaussians come in. What I want to say now is that this form of a quadratic polynomial is the most general form under the Gaussian distribution. In other words, okay, consider a quadratic polynomial. Let's say it has no linear part. Then it's of the form x transpose Ax, where A is a symmetric matrix. But because Gaussians are rotationally invariant, I can recap one line. So consider a quadratic polynomial x transpose Ax. Because Gaussians are rotationally invariant, that means I can diagonalize the matrix A, and if the corresponding diagonal matrix is lambda, then the distribution of x transpose Ax is the same as distribution of x transpose lambda x, which is same as saying summation lambda I xi square, which we already know looks like a normal if all the lambda i's are relatively small. And as a consequence of this and the rotational invariance of Gaussians, we get that the distribution of x transpose Ax differs from a normal with the correct mean, which is now trace of A, the sum of the eigenvalues, and the variance of this polynomial, which is twice Frobenius norm of A square, as long as all the singular values of the matrix A are reasonably small. Okay, we don't have a linear form so far, but really this is the part where the rotational invariance of Gaussians comes in so handy. So quadratic polynomials of Gaussians will look like Gaussians unless there is a large singular value somewhere in the matrix. In fact, in this earlier paper with Ilias Diakonikoulos, we proved that if you add a linear part, so intuitively if you add a linear part, that should only make the thing more Gaussian, because linear function of a Gaussian is a Gaussian, so that should intuitively not hinder asymptotic normality. And indeed it's true that if you add a linear part, then then x transpose Ax plus Bx differs from a normal with the mean, the correct mean and the correct variance, as long as the singular value of A is small, not just compared to Frobenius norm, but you get to divide by the 2 norm of the linear part as well. And that's obvious, right? I mean, if you are adding a huge linear component, that should only favor asymptotic normality. In fact, we prove not just closeness in Kolmogorov distance, but in total variation distance. So it's like L1 distance between the laws. So that's a really strong metric. I'm going to come to the proof of this part. That's going to almost require the whole machinery. But for the moment, let me say, okay, so we understand at least in some distance, we understand what quadratic distributions of quadratic polynomials look like. Under what conditions do quadratic polynomials look like Gaussians? And in fact, this is a tight condition. If one of the singular values is very large, for A, then you can show x transpose Ax is constant far from a Gaussian. So the singular value of the corresponding matrix really captures, the other part is not hard to show, that x transpose. So the large singular value really captures how far a quadratic law of a quadratic polynomial of Gaussian is far from a Gaussian. Okay, but now I want to think about higher degree polynomials. And what really worked for us in case of quadratic polynomials was the rotational invariance of Gaussians, which will continue to hold good, and very critically the fact that the matrices can be diagonalized, which is no longer going to hold good. Okay, so
what is dk?
oh, dk meant Kolmogorov distance between x transpose Ax and, so Kolmogorov distance just the probability, the L infinity distance between the laws of the polynomial, the CDFs. And okay, so now we want to know what happens to higher degree polynomials. So before I answer what happens to higher degree polynomials, okay, what happened? Oh, I have that written down. Excellent. So let's try to understand when is a distribution of a higher degree polynomial not close to a Gaussian. And then maybe hopefully we'll cover all the cases and whatever remains will be close to a Gaussian. So one case when a distribution of a higher degree of any polynomial won't be close to a Gaussian is, suppose Px is a polynomial and Px actually factorizes in the form Qx times Rx, where Qx and Rx are both non-trivial, so they are both of degree at least 1, if not more. Then it's not hard to show that the law of Px is omega 1 far from any normal. Mainly because Px will have huge moments. The fact that it factorizes basically captures that it will have huge moments. The moments of it will look very different from moments of a Gaussian, and that can be used to show that the law of Px is omega 1 far from any Gaussian. In fact, a robust version of this statement is also true, that if Px correlates very well with Qx times Rx, where, okay, I have not written the conditions, that Qx and Rx are both of degree greater than 0, so they are not constants, and the degrees of Q plus R is equal to the degree of P. Okay, and we are normalizing everything. So variance of P is 1, variance of Q is 1, variance of R is 1. So if we can find Q and R such that their variances are also 1, and the sum of degrees is D, and they are both non-trivial, they are not constants, and the correlation is at least epsilon, then the law of Px is omega epsilon 1 far from a Gaussian. So this is a hindrance. If a polynomial correlates well with product of lower degree polynomials, it is far from a Gaussian. And in fact, this should correspond well to the quadratic part, because earlier when we were thinking about the quadratic polynomial, we said the maximum singular value, is it large, is it small? The maximum singular value really captures the correlation of a quadratic polynomial with two linear forms, two forms of lower degree. And that hindrance continues to reflect itself in higher degree polynomials as well. The question we want to understand is this the only obstruction towards asymptotic normality? So suppose it happens that a polynomial P is uncorrelated with product of lower degree forms. Is that sufficient for closeness to normality? And if so, with what parameter, translation of parameters, and how do we understand the correlation with lower degree forms? Is it something computable? We will require it to be computable. And all these questions will answer now. Okay? And for understanding all this, we will require the language of tensors. Yes?
So far, have you discussed any, so x squared is far from Gaussian, but it's not multilinear. Multilinear with the original polynomials that we
X1, X2 is far from a Gaussian. Yeah, but because of this rotational invariance in the quadratic in Gaussian world, multilinear, we are not going to split hairs about that. Okay, it's almost all the same. But I understand. Okay, this is a good question. Like we are starting with multilinear, we went to non-multilinear, but yes, Eddie, you have a question?
Yes, so is there a statement compared to the one you have below that for trilinear forms?
Sorry?
If you lift this board,
Yes.
is a statement about trilinear forms and a condition for them to behave like Gaussians?
Yes, so that's the hard part. Like this was easy to show, right? I mean, this part, at least in sums, was easy to show. That's what I was saying. Like a harder thing once you look at higher degree polynomials, if there is no ready-made notion of eigenvalue, even if there is, it's not clear how. Like you can't diagonalize trilinear forms.
Sure, but there are special cases that you could.
There are special cases you could. We will go for the most general thing. We will give a necessary and sufficient condition which will cover all polynomials, all trilinear forms. For that, I need to define the appropriate notion of a maximum singular value of a trilinear form of of like any d-linear form, and we'll show that number actually is computable and it captures closeness to a normal. Okay, but for that I need the definitions correctly first. Okay, but yeah, that's where I'm going, like how to capture things for trilinear or higher degree forms. Okay, so for that, so I'll require the language of tensors, and now this will be slightly notationally heavy, but I think it pays off. The notations pay off as usual. Okay, so what we'll do is, for the moment, just consider homogeneous polynomials. Okay, let us consider homogeneous polynomials. So homogeneous quadratic forms map to matrices. So homogeneous degree D forms should map to tensors. So yes, so homogeneous degree D forms will map to symmetric tensors. Okay. Good. It will map to symmetric tensors. So what is the mapping? I will actually, this correspondence goes through for non-multilinear things as well. I mean, there's a complicated way of explaining this, and there's a simple way of explaining this. Let me go for the complicated one. No, it's easier to explain the complicated thing. Okay. Okay. So how do we do what is the mapping we want to understand? Okay. So we want to map polynomials of homogeneous polynomials of degree D and homogeneous and symmetric tensors of order D. Okay. And how do we want to do that? So for that, I need to first define what Hermite polynomials are. So for univariate Hermite polynomial, h0x is 1, h1x is x, and in general hq of x is minus 1 to the. I was enjoying writing with a pink thing, but it's good while it lasted. Okay, this is the formula for Hermite polynomials. I'm sure all of you know that. Okay, there are several normalizations people use, and the way we have normalized things, the thing is that if you consider the Gaussian distribution, if you consider, okay, this is right now only a univariate x n 1, hq of x, hq square of x is 1 over q factorial. This is the normal, this is the, I mean, if you remove a q factorial from here, it will become q factorial. If you can put square root q factorial, then it will become 1. This is the normalization we have used. Okay, these are Hermite polynomials. No, any questions? Yeah, this is a single variable for now. Now I'll define multilinear Hermite polynomials. Okay, so now next I'm going to define the mapping between polynomials and tensors. Sorry, this one. If you, it's a polynomial in x. No. This is a formally a polynomial. If you take e to the x square over 2, keep this thing. When you look at this thing, it's e to the minus x square over 2 times some polynomial in x. Sorry? Yes, e to the negative x square will multiply with the e to the minus x square over 2 will multiply with e to the x square over 2. If think about taking the first derivative. Okay, h0x is 1. Think about taking the first derivative. What is the first derivative of e to the minus x square over 2? It's e to the minus x square over 2 times minus x. So e to the minus x square over 2 will multiply out and you will kill the thing. You take two derivatives of e to the minus x square over 2. You will get e to the minus x square over 2 will always remain there times some polynomial. A polynomial. No, this is dx to the q. This is like just taking the qth derivative. Oh, this is a polynomial, okay. Now I'll define the mapping between tensors and polynomials, okay. And this is noted as I sub q. The notation comes from stochastic calculus. This is called the iterated Ito integral, but we don't care. So look at E1 tensor, E1 tensor, E1. This E1 is the standard unit vector with 1 in the first position, 0 everywhere else. And now I look at this symmetric tensor. Eddie, do you agree this is a symmetric tensor? Absolutely. Okay. And this is equal to q factorial times hq of x1. Okay, so I have just defined it for one thing. I've just defined it so far for one variable, how to do it. Okay. Now what we do is, in general, if you have a unit vector v tensor v q times then instead of taking hq of x1, you put v dot x inside this thing, okay? You will get another polynomial, right? This is the mapping for these rank 1 tensor forms. And any symmetric tensor can be written as a linear combination of rank, any symmetric tensor can be written as a rank 1 combination of linear, as a linear combination of rank 1 symmetric tensors, got it. You just extend the map linearly, okay? This covers the entire, this defines the mapping between entire space of symmetric tensors and polynomials.
So here, the v, it's a vector, x is a vector. Are you doing an inner product?
What v is a unit vector? Yes. So this is a symmetric tensor?
Sure, no.
And v dot x is just summation vi xi. Okay. So by extending this map linearly, we have defined, we have consistently, okay, you can show it's consistent easily, that we have consistently defined how to map the space of symmetric tensors to degree q Hermite polynomials. So whenever I now talk about degree q, it's not degree q in the standard sense, it's degree q in the Hermite sense. That means a polynomial is said to be degree q in the Hermite sense if it's spanned by the set of Hermite polynomials, if it can be expressed as a linear combination of Hermite polynomials. Is the mapping clear? Is the mapping, does the mapping make sense? Yes.
Okay, so this is definition of mapping?
Yeah, this is the definition of the mapping. I've just defined the mapping. Why did I define the mapping this way? The mapping, the reason, okay, okay, so the important thing is, okay, so suppose you were considering, this is all for non-multilinear things, right? This is all for non-multilinear. This is for multilinear, non-multilinear, works for everything when you define this map symmetrically. When you define this map, it works for everything. For multilinear things, it's very simple. For multilinear things, what it will become is that if you consider a multilinear symmetric tensor, meaning all terms in which the same indices appear at least twice will be all 0. So that's the multilinear symmetric tensor. And they, when you consider this mapping, then it will just be a scaled version of the monomial corresponding to, like you just basically just look at the obvious polynomial you construct out of that. If you take a multilinear symmetric tensor, you write down the obvious multilinear polynomial and you have to scale by 1 over q factorial or something. So consider matrix. This is a multilinear matrix because all the diagonal terms are made 0, and the obvious mapping is x1 x2 because only x1 x2 is 0. Suppose you consider the matrix which is 1 0 2 1, this is, then this is x1 x3 twice x1 x3 plus x1 x2. This is the obvious mapping. Okay, and you have to scale it because this factors introduce some scaling here. So I think you get to divide by q factorial.
So wait a minute, you're saying these two mapping are equivalent?
Yes, for multilinear, this mapping that I just did was for multilinear. This doesn't say what to do for non-multilinear symmetric tensors, but when you do this mapping, the thing you for the multilinear symmetric tensors, it will be exactly the obvious mapping.
So you're saying they match for multilinear, but away from multilinear polynomials?
This is the map. Away from multilinear polynomial, okay, if I had 1 2 2 1, an obvious mapping would have been x1 square plus twice x1, x2, or maybe 4x1, x2 plus x2 square, right? This would have been a obvious mapping, but this is not the right mapping. For multilinear it will match, but for non-multilinear this is not the right mapping. This creates some other mapping for non-multilinear tensors.
They are far apart.
They are far apart meaning? Oh, they look different. Yes, they look different. At a constant fraction of places they will look different.
So they're going to be orthogonal?
They are going to be orthogonal, yes. The reason is, let me go to the next part, and then it will probably become clear why this more complicated mapping.
So that's a quick question.
Yes.
You can define this by putting into your e to the negative x squared covariance matrices.
E to the minus x square, instead of you're saying, what if I did e to the minus x transpose sigma x or something?
Yes, exactly.
I don't even know how to take the derivatives then.
These are polynomials. Do exactly the same trick you did. You're going to compute derivative with respect to each one.
Okay.
Would that be equivalent?
I don't know. Maybe. I don't know. I don't know. Maybe it will be. Yes. Okay. Maybe it will be, but I don't know. The reason why we created this mapping is the following very important thing, is that this is an isomorphism in the following strong sense, that e to the iq, if you take any symmetric tensor, let's call it h, times iq of h prime, another symmetric tensor, that is equal to q factorial h comma h prime. So we have created an isomorphism. This kind of a mapping, what will ensure is that the inner product between these polynomials in the Gaussian world is equal to q factorial, so up to some scaling, the same as the inner product between the corresponding tensors in the standard when you take a inner product of two tensors, which is like the term-wise dot product and sum it up. Okay? So this basically creates a mapping between the two geometries, which is very critical for us. This is not a hard proof. You can prove it by induction or something. Like once you know. Yeah, this is orthogonality. No, this is, yeah, this is orthogonality. Just proving this thing, you can prove it by induction. I'm not sure what you mean by orthogonality. Yeah. Okay. Yeah. You can prove it by induction. Okay. You can prove it by orthogonality. Yeah. I mean, I'm not even sure what name to give it. Like, it's easy to prove this thing. Okay. So. Okay. So this is great. Okay. Now, next comes contraction products between tensors. So now we understand why we want to talk about polynomials in terms of tensors, because of this geometry preserving thing. Now comes contraction product between tensors. Okay. Let f be a symmetric tensor of order q, which I denote as by dot q, meaning it's a symmetric tensor of order q. It's a symmetric tensor. Oh, by the way, just symmetric tensor just means if you permute all the coordinates, the tensor remains invariant, like a symmetric matrix. If you change the row to columns, the columns to row, the matrix remains the same. So, in case I wasn't clear. So you take two symmetric tensors. Then the contraction product between the two tensors, which we denote by f tensor s g, a contraction product of order s, is basically okay, it's a symmetric tensor of order q. So you flatten it out, okay? You make a matrix out of it with project s of the first s indices on the rows, or first q minus s indices on the rows and s indices on the column. Okay, you can always do this. You can just flatten it out. And because it's a symmetric tensor, it doesn't matter which s indices you choose to flatten out. So you make project s of the indices on the columns, q minus s of the indices on the row. Likewise, here you choose s indices on the rows and r minus s indices on the columns. Now there are two big matrices, f q minus s comma s and g s comma r minus s, just denoting the partition. Take the product as a matrix multiplication, and you get a big tensor of size q minus s times r minus. You get a big matrix of size q minus s with q minus s rows and r minus s columns. You can now remap it back on tensors, and this is an element of H q plus r minus 2s. Note, I can take two symmetric tensors, I can do a contraction product, and they need not be symmetric. Much like I can take two matrices, multiply, two symmetric matrices, multiply, and the outcome is not symmetric. A times B need not be symmetric if A and B are both symmetric.
How do you unflatten?
Because you just identify the first q minus s rows with with the first the rows with q minus the first q minus s indices, and the columns with the next r minus s indices. Most of the times we will then symmetrize the tensor, so it doesn't matter.
You don't need to do this packing and unpacking, just summing over matching pairs of passing bases.
Exactly. I just wanted to say visualizing how do you do it. You don't need to do the packing and unpacking, but this is how, and the reason I have not put dot here is because it need not be a symmetric tensor. Okay. But I can always also, there is another operation of symmetrization of tensors, which just means take a matrix and take the tensor and symmetrize it, meaning look at all possible permutations of the indices and then average it out. The same way you symmetrize a matrix. So nothing more going on.
But so this is expensive if your tensors of order n.
Oh, but here the tensors of order d, which is a constant. And again, like d, okay, yeah, it's n to the d. It will be, the running times will be like n to the d, n to the 2d, doesn't matter. Okay, now comes a very important formula. So as I said, this tensor notation comes from Ito's calculus, which is like a stochastic calculus, and this is Ito's multiplication formula, which is very important. It's easy. It's not hard to prove this thing. I don't know how to. I mean, this should be provable by induction. I've never tried to prove it. That if you have a tensor of order, consider IPF. So f is a tensor. IPF is the corresponding polynomial, and consider IQ of G, where G is a tensor and IQ of G is a corresponding polynomial. So this is a degree P Hermite polynomial, this is a degree Q Hermite polynomial. That I want to express it in terms of what happens on the operations on the tensors. R equals 0 to min P comma Q, R factorial, P choose R, Q choose R, I P plus Q minus 2R, F contraction product with G, and then you symmetrize it. So basically, this multiplication formula, it's easy, it's not hard to prove this thing. But basically it says, if you are taking two polynomials, what happens, what is the product polynomial in terms of the corresponding operations on the tensors? Okay, it's an equality, cannot be super hard to prove. I've never tried to prove it though. Okay, so now I have written what is Ito's multiplication formula, and now I think I have introduced enough notation that I can write down the statement of the central limit theorem. Okay, I had planned that at this point I'll be doing half of the proof, but okay. So we have understood the mapping between polynomials and tensors and some connections between these things. Now let's try to define the singular value of a tensor, the way what is desirable to us. Okay, and the way we will define it is very, very simple. So let A be a symmetric tensor. Always writing it as H in P. H is just the Hilbert space, so it's like R to the n, but just consider symmetric tensor A. Now consider a non-trivial partition of P. So P is for us is like D, but consider non-trivial partition S, P minus S. So you consider non-trivial partition of P. And now consider the flattening A, S, P minus S. You consider the flattening. Now this is a matrix, you can look at its singular value, the maximum singular value. And sigma max of the tensor is simply equal to maximum over S p minus S, which is such that they are both non-trivial, meaning the size of this thing, the product of the sizes is greater than 0. So, you are considering a non-trivial partition. Sigma max of A S comma p minus S. So, this is the notion of maximum singular value we are going to use. And if this number is small compared to the Frobenius norm, then we will say it's eigenregular. Okay? And yes,
This is you're maximizing over all the matrix flattening.
all non-trivial matrix flattening. So, you have to at least put one index on the row and at least one index on the columns, and then look at the maximum singular value. Okay? And with this, we have the theorem, which is the main central limit theorem, or at least the first version of the central limit theorem. So, let f be a degree d polynomial. Okay? So far we were considering just homogeneous polynomials, but in general the polynomial is non-homogeneous. And let us just assume the mean is 0, so the constant term is 0. And now let f be the polynomial, and that we symbolically express as I1 of f1. So, I1 of f1 captures the linear part, the Hermite linear part, as I2 of f2, da da da, ID of fd. Okay. So, we split it, this is efficiently doable, and now the total variation distance of f, the law of f from, so let us assume that the variance of f is 1, you can normalize that, from a normal is at most, okay, up to factors dependent just on d, and this is like d factorial or something, maximum of I equals 2 to d sigma max of fi. That's it. So, you are saying if earlier we just looked at the singular value of the quadratic part, now we are saying okay, if all, not just the quadratic but all the parts, the singular values are small from f2 to fd. Again, linear parts should not hinder asymptotic normality, so we do not consider to first part. If all these values are very small, then this law of f is very close to a normal, and this is like up to constant factors, up to the factor of d here, this is tight. The upper bound is a hard thing to prove, the lower bound is not that difficult to prove.
The matrix case you were dividing by something.
The matrix case I was dividing by Frobenius norm of A, which is roughly the measure of the variance. Here I have just assumed the variance is 1. If you wanted to, if I have just assumed the variance of f is 1, since I have not written that, if you want you can divide it by the Frobenius norm of f1 plus f2 plus so on, which is like the sum of squares of the entries. But if you assume the variance is 1, then these are constant numbers. Yes, Andy?
Is there some notion that these flattenings, these splittings, this partition to S and P minus S, is that analogous to
The fact, yes, 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 yes. Sorry? No, I have not proven that. I have not yet proved that. But intuitively, yes, I'll write out the lemma, and if you know Ito's multiplication formula and all this, it's easy to prove that it's exactly the same thing. But basically, yes, this, what I did not show, what I haven't written till now is that this sigma max fi basically captures the correlation that the degree I part has with product of two lower degree forms. So, yes, in the concrete sense, the question we started out with, asymptotic, that is non-trivial factorization the only hindrance towards asymptotic normality? The answer is yes. Of course, we have to put in a lot of, I mean, one thing is that you have to define clearly what you mean by this being the only hindrance, so, or define it clearly.
So, in the argument, there was this so-called natural mapping and the Hermite polynomial.
Yes, yes.
And the two can be viewed as different bases for encoding polynomial.
Which two?
The
One
natural
is the
mapping-
one is the tensor world, and another is the standard polynomial. Yes.
So, what are the properties of the Hermite polynomial construction that we crucially use?
So one thing is that Hermite polynomials are all orthogonal. So like, you know, I mean, HQ of HQ of x1 times HP of not x1, HQ of V times x times HP of W times x. Doesn't matter what W and V are. If Q and P are not the same, then the inner product is 0. The expectation of the inner product is 0. The expectation of product is 0. Okay, so
if I had used the original basis, done Gram-Schmidt on these guys to obtain a new basis, would this property carry?
I think yes, if you do Gram-Schmidt, you will always have the orthogonality property. But there are other nice things which happen once you, like, you can express it exactly what's happening in terms of the mapping between polynomials and tensors. I don't know how much of it will carry if you just did Gram-Schmidt. Maybe, I mean, okay, if you just consider the standard basis, maybe these factors, some of these factors will go away, but then some other complications will come in. It's one thing, the reason you do this, consider this particular mapping is the same reason in Gaussian processes you consider, the same reason in Gaussian processes you map linear vector, you consider the isomorphism between vectors and Gaussian random variables, because the geometry is preserved. The geometry of the Hilbert space gets reflected in the stochastic properties of the Gaussian process, and it's easy to relate. And then it's just get a geometric tool to argue about probabilistic things. Maybe you could have chosen some other basis and it would have worked fine, but this is the standard basis to choose.
Okay, and is this eigenfunction for the always random on the operator?
The Hermite polynomials, yes, they are, right?
Yeah, okay, so there are canonical always. So what operator are the eigenvectors for? Always random on the canonical operator.
Don't ask me to write down the operator. I don't know how to write down the operator in that.
Okay, you take two triangles which are correlated, then you take interpretation of one of them, and that's like you add some noise, and you capture the eigenvector, that you get these things.
Okay, so which part should I can probably erase that part now. Okay, so there is absolutely no way I'm going to finish the proof of the central limit theorem today, but let me just write down the statement Andy was referring to, that product of that these singular values correspond to the non-trivial factorizations, which is the following. Up to constant factors. Let me write down the statement. So let P, again R2 N2 R, be homogeneous. Okay, let be Hermite homogeneous. H and variance is 1. Okay. Look at the soup of P times Q times R, expectation of P times Q times R. Again, it's over standard normal, where variance of Q equals variance of R equals 1, degree of Q plus R equals D, and both of these degrees are greater than equal to 0, greater than 1, greater than equal to 1. So degree of Q times degree of R is greater than 0. You look at this quantity, what is the best correlation you can have with P with product of lower degree forms? That up to constant factors is just sigma max of the tensor corresponding to P, which I write as AP. And in fact, it's a constructive proof, meaning because sigma max of AP, the way I have defined this, is very easy to compute, right? You consider all possible non-trivial flattenings, which takes time 2 to the d, d is a constant, and then you consider the singular values. That's easy to compute, 2 to the d times n to the d. Then that itself will get not just give you a certificate, but it's actually constructive proof. It will give you polynomials which correlate with, it will give you Q and R which correlate with P. Very intuitively, the polynomials you will get are that look at the flattening which is exhibiting the largest singular value, that will, and the corresponding largest singular vectors that naturally maps to polynomials of to smaller degree, and you can actually show after some manipulation, basically using this Ito's multiplication formula. I had the proof, but I have the proof, but
So you're saying you consider all 2 to the d versus that it's symmetric, so I would have to consider like d minus 2 choices?
you're saying, well, I have to only consider. Yes, excellent, yeah, I don't even have to consider 2 to the d. Well, the matrix is of size n to the d, so you will pay something like that anyway, right, because it's symmetric, you don't have to consider all possible subsets, you just look at the size of the subsets. So that's d choices or d minus 1 choices and times n to the d. And once you get the singular values and the corresponding singular vectors, those also give you the factors.
So is there a similar statement if I have polynomials from Rn to Rm?
Those will be like r to the n to r to the m, that will be like m different polynomials, right?
Yes. So if I have some statement about sigma max over all dimensions, can I do some factorization?
Not sure.
I can ask you later.
Yeah, I'm not sure like what you define as factorization in that, since you'll have to define.
Sure.
Okay. Okay, so I have 10 minutes remaining today. So I can do 2 things. I can try to say what sigma max, how you prove this theorem, how do you prove this lemma, which is not super important, or we can try to get into how the sketch of how do we prove this theorem. I can't prove this theorem possibly in 10 minutes, but at least tell you the basics of Stein's method.
So could you prove the lemma?
Stein's method? Okay, you're always going against the majority. That's not good.
No, go with the majority. We go ahead.
Okay, let's try to. Okay, so if you don't care about Gaussian polynomials, again, the good thing about this is there are multiple entry points here. Maybe you care about Stein's method. Okay. So what are we trying to understand? We're trying to understand when is a polynomial of Gaussian close to a Gaussian. When is a random variable close to a Gaussian? How do we prove a random variable is close to a Gaussian? And one of the most, of course, sum of independent random variables looked like a Gaussian. That's central limit theorem. There are Fourier methods of proving this, n number of ways of proving this. But surprisingly, those methods start failing if we are not dealing with sums of independent random variables. Here, we are dealing with a polynomial of Gaussians. Forget about polynomial of something, we are dealing with a polynomial. That's like summing up highly dependent random variables. And probably one of the most versatile tools for proving central limit theorems was given by Charles Stein, I think, Stein's method. And it's based on the following very interesting identity, which is trivial to prove, but I think is very amazing. Is the following. Look at the standard normal. And now let f be such that it's differentiable once and both the function and its derivative are bounded. Okay. Then expectation over x in z f prime x equals expectation x in z. Okay, you know what? I'll just minus x of x equals 0 for every function f which is like nice. I think you actually require just f to be absolutely continuous. F prime x minus x of x is always 0 when you take expectation. How do you prove this? Integration by parts. Let me prove this for fun. So f prime x minus x of x times e to the minus x square over 2 dx, right? So let me just try to just see what this part evaluates to. F prime. So that I can say is equal to, I can take out df, I can put dfx here by integration by parts, and then that's fx e to the minus x square over 2 minus infinity plus infinity, and then plus. So this term is 0 really, at minus plus infinity this becomes 0, and then you have fx times x times e to the minus x square over 2 dx. which is exactly this thing.
Could you also just see that as Taylor series?
Sorry?
Could you also just look at the Taylor series and show the parts that are contributing to this expression? Can you tell that that is?
Look at the Taylor series of what? Fx?
Well, start with the Taylor series of F and think about the transformations on that series, differentiation and then.
I think it probably should be true. Yeah, if you look at the Taylor series, yes, it should be true. Anyway, this is like the slickest way to prove it. Okay, that's great. So f is always this operator. So you take a function a and consider this operator a, which acts on f as f prime minus x of x. This operator is always 0 if you take expectation into the Gaussian. That's amazing. And turns out that this operator is also a characterizing operator for the Gaussian, meaning if there is a distribution z such that this is always 0 for every f which is bounded and its first derivative is bounded, z must differ from the standard normal at only a measure 0 set. Okay. So since this is the few places I'll ever get to use calculus, let me write down. So the way you prove that is actually just basic ordinary differential equations. So what you do is you say, I'm considering f prime x minus f x of x. So let me let me have a function gx, okay, and I want to solve the differential equation f prime x minus x of x. And I also want a property that limit x tends to infinity, fx minus infinity, fx times e to the minus x square over 2 equals 0. So I want some nice solution to this differential equation. Okay. And if you know differential equations, it's not hard to show that the solution f of y equals e to the y square over 2 times integral from minus infinity to y e to the minus x square over 2 times gx dx. Okay. And now two things you can prove about this solution. One is that if f is bounded, this function is also bounded. Sorry, if g is bounded, this is bounded. In fact, something else is true. If g is bounded, this function is differentiable and its derivative is bounded. So that's very good. Like you start with potentially just function which has only kth order derivatives, and you end up with a function which also has k plus 1th order derivatives. This probably is a very subtle reason why Stein's method is so interesting, because just out of solving this differential equation, you get a function of one higher order smoothness than g has. Okay. Okay. So now, what do I do? Okay. So now, okay. So we are trying to prove that the function that suppose there is a set. Suppose we have solved this differential equation. Okay, and now we are trying to prove that w, that if there is a random variable such that expectation of w times gw minus g prime w is 0 for all g such that the first function and its first order derivative is bounded, then w must be the normal. That's what we are trying to prove. Okay, so how do we prove this? So if w differs from a normal on some set larger than measure 0, there must be a bounded function which exhibits this difference. There must be like a Borel measurable set. That means if suppose w and z are the standard normal differ, then there must exist actually write f and f. Now suppose w is not equal, the law of w and z, the standard normal differ, then that means there exists a function g mapping r to let's say 0, 1, such that expectation of g of w minus expectation of g of z is greater than 0, right? Now consider g of actually sorry, this is I said something wrong here. This function is bounded if the expectation of g over the standard normal is 0. If the expectation of g over the standard normal is 0, then this function is bounded and has first order bounded derivative. It's not that if g is bounded this will happen. Now expectation of gw minus gz. So consider gw minus expectation of gz, call it h of w. Clearly this is just a function of w. This is bounded for obvious reasons. Furthermore, the expectation of h over the standard normal is 0. Then it means that if I consider f prime w minus w f w equals h w, then it admits, then I can use this differential equation and I can say that there is a solution to this differential equation which is bounded and whose first order derivative is bounded. So let f be that solution, and now expectation of f prime w minus w f w must be equal to expectation of h w, which is actually expectation of g w minus expectation of g z, which according to hypothesis is greater than 0. On the other hand, we assume that for all functions f which are bounded and first order derivative is bounded, this function must be equal to 0. There is a contradiction. That means this operator characterizes the normal. In fact, we got something more, that if you just look at this proof, we get that the total variation distance, suppose we are looking at the total variation distance of w from the standard normal, that the exact same proof says it must be equal to the sup of f prime w minus w f w, where the function is bounded and the first order derivative is bounded. In fact, you can put the actual bounds there. It's like 2 and root 2 over pi or something like that. So just take it to be 2, that the maximum distance that w has from the standard normal is equal to sup of absolute value of expectation of f prime w minus w f w for all f's which are bounded by 2 and whose first order derivative is also bounded by 2.
Are you saying that that method is like complete?
Yes, I think so. I mean incomplete in some sense, yes.
Could you give like the simplest example you know where that method is useful? To be honest.
Simplest example I know. This is an example. I think like suppose consider you are summing up random variables, Bernoulli random variables, okay, and they are not independent, they are dependent. But how are they dependent? The dependence is of the following form, that every variable is only dependent on you have a graph of size n, and there is a dependency structure which you indicate by the edges, and this graph has, every vertex has degree, let's say a constant, or even like something polylogarithmic in n, or even some small polynomial in n is also okay. And you want to know, does the sum of these random variables still behave like a normal with the same mean and variance? And the answer is yes. Stein's method will allow you to prove this. So you can prove sums of weakly dependent random variables to also converge to Gaussian in some metric. It need not be sometimes as strong as total variation distance. This is also very versatile, because while I showed something for total variation distance where I said you have to understand the sup of f prime w minus w f w for f which is bounded and its first order derivative is bounded. If you want to prove a weaker metric, you can assume f is bounded, the first order derivative is bounded, and the second order derivative is bounded. So it's like an even smaller class of functions. So this is there's like a whole industry in this, like in people, it's very versatile. But I think the simplest example, and which is where Stein came from, is in this method is trying to understand the sum of slightly dependent indicator random variables, where any two variables are dependent if they have a common edge, and you know, I mean, so just consider something like summation xi xj. You have a graph, and every vertex has an independent random variable xi, and now you consider the sum of xi xj over all the edges. That's a weakly dependent random variable. You want to understand, is if the graph is of constant degree or something, is it true that the sum behaves like a norm? It's really dependent. There's a conservation of difficulty here, so it's not going to become ridiculously easy. But I don't know, without using Stein's method, how to even go about proving this thing. Here, it's like, okay, now you have to understand expectation of f prime w minus wfw. So then there are like several methods of how to analyze this sum. One is like the Stein pair thing. Another is like you try to expand you try to understand, you try to do some sort of a Taylor's expansion of w and see how much change is going on. It really depends on the question per se, but there are places where without Stein's method, I don't think there's any other proof known to work. This also being one of the places, I don't think there was any. This whole there was whole like lot of. I mean, it's not like our theorem that we are stating here is the first theorem about convergence of Gaussian polynomials to normal. There were other theorems in similar flavor, not of the same kind and not the characteristics we want. But again, in those cases, I still don't know how to prove that. How to even start proving? Like, I'm not sure how to start proving. It really depends. I think I should stop here. I didn't get to the proof, but I guess, yeah, I was not hoping. Okay, thank you.